Hello, everyone, and welcome to this week's lecture on foundational statistical concepts in educational research. Today, we will explore some of the most essential tools used in descriptive statistics. Concepts like measures of central tendency, variability, distribution shapes, and the impact of data transformations. These are not just mathematical ideas. They shape how we understand learning, teaching, and equity from early childhood through higher ed. Let's begin with measures of central tendency. These are ways to identify what is typical or average in a dataset. The three main measures we often use are the mean, the median, and the mode. Imagine you're looking at the number of sight words known by preschoolers at the start of the school year. In a class of 10 children, perhaps most children know around 15 to 20 sight words. But there's one child who knows over 80. The mean, also known as the arithmetic average, would be pulled up by that one high number. The median, however, which is the middle score when all scores are lined up in order, would give a more accurate picture of what is typical for most students in the group. The mode, which is the most frequently occurring score, might help you see if several students are clustered around a certain level. Maybe five of them know exactly 18 words. In the case, 18 would be the mode. So, depending on what kind of data you're working with, one measure of central tendency may be more appropriate than another. For example, if you categorize students by their favorite color, say in a kindergarten classroom, you cannot calculate a mean or a median. Those are numerical operations. You would use the mode since you are just identifying the most common category. Now let's talk about variability. While central tendency tells us what is typical, measures of variability tell us how spread out the data are. The range is the simplest of these. It's just the difference between the highest and lowest scores. For example, in a 10th grade classroom, if the math test scores range from 55 to 95, the range is 40. But that alone doesn't tell us much. Two classrooms could have the same range, but very different patterns within that range. This is where standard deviation and variance come in. These measures tell us how far individual scores tend to be from the mean. For instance, in one classroom, most students might score near the average of 75, while in another classroom, students are either scoring in the 90s or the 50s, with few in between. Both classrooms might have the same mean score, but the second one has a much larger standard deviation. That would prompt the teacher or researcher to look more deeply into students' needs and instructional approaches. Now let's explore the idea of distribution shape. A normal distribution, often called a bell curve, means that most scores cluster around the center and fewer scores occur as you move toward the extremes. This pattern is common in many large-scale assessments like the SAT or state reading tests, where we expect most students to perform near the middle and only a few to score very low or very high. But in real classroom settings, we often encounter skewed distributions. A positively skewed distribution means that the tail is stretched out to the right. This could happen if a test is too hard and most students score low, with just a few scoring high. A negatively skewed distribution stretches left, maybe in a case where a test was too easy and most students scored high. Understanding skewness can help educators choose or revise assessments to better match their students' current level of understanding. Let's talk about transformations and how they affect our data. Say you're evaluating the progress of a small reading group in second grade, and you decide to add 10 points to everyone's score because the original test was too hard. This is called a linear transformation. Adding a constant to all scores increases the mean and the median by that amount. but it does not affect the standard deviation or variance. That's because everyone's distance from each other remains the same. But what happens if you instead multiply everyone's scores by a constant, like scaling scores for a standardized test? In that case, both the mean and the standard deviation change. So, when interpreting data, especially transformed or scaled scores, we have to be mindful of what the numbers really represent in context. Now consider a high school class where students take an end of unit test. Suppose a few students score far below the mean. These low outlier scores can bring down the overall average significantly, even if most students did well. These outliers also increase the standard deviation because they add more spread to the data. In real classrooms, this might prompt a teacher to offer additional support or revisit certain concepts. On the other hand, what if several new scores are added that are right around the mean? That would have little impact on the mean or median, and it would slightly decrease the standard deviation because those scores are not increasing the overall variability. This is often what we aim for in instruction, bringing more students closer to the typical performance level. We also need to understand ceiling effects. These happen when a test is too easy and many students hit the top score. For example, a pre kindergarten counting assessment might top out at 10, but if many children already counted 20, the test will not show what they can really do. This masks true differences among students at the higher and flattens your data. Let's wrap up by revisiting variance and standard deviation. Variance is the average square distance from the mean. It's a way to measure spread. Standard deviation is just the square root of the variance. So it's in the same units as the original data. In educational settings, standard deviation is more intuitive because it reflects how far scores typically deviate from the mean in the same units, like points on a test. Understanding these foundational statistical ideas equips us to read research more critically and design assessments more thoughtfully. Whether you're working with preschool readiness scores, elementary reading levels, middle school science labs, or high school college prep exams, these tools help us make data driven decisions that are grounded in the realities of teaching and learning. Thank you for watching, and I look forward to continuing our exploration of statistics in education next week.